Okay, my name is Minjun Kim, and I'm starting the presentation of reinforcement learning project. First of all, I'll talk about my training settings, and the common training setting are as follows. Others are same as baseline, and the number of episodes is 2000, and I initiate alpha with 0.2, and network is same as the baseline code, and learning rate of actor and alpha and critics is as written in this presentation. So the first task was standing long jump. For extra training setting, I put max torque 5.0 to get more strength enough to jump. There are 4 reward functions. The first one is front jump reward function. It computes the dot products between the change in the snapbot's position and its local x-axis to determine, from the robot's perspective, how far it has traveled forward. Even if its orientation drifts relative to the world frame, this method ensures the forward jump can be learned accurately, allowing stable training across multiple consecutive jumps within a single episode. Additionally, the reward is only applied when all 4 legs are off the floor, which means it is airborne. The second one is vertical velocity reward, and it's proportional to its velocity along the z-axis. It is used only when the value is positive, which means going up in the jump situation is only contained. The third reward is soft rollover reward, which applies a penalty when the angle between the snapbot's local z-axis and the world z-axis exceeds 60 degrees. I use this because I want snapbot to jump in a stable manner. The last one is collision reward, which gives penalty if there is a self-collision. And for the result of the first task, the final model achieved a jump distance of 0.46 meters along the x-axis. This distance is measured from the moment all 4 of the snapbot's legs leave the floor until the moment any one of them touch the floor again. And from the training and experiment, snapbot learned to lift its front leg and jump forward using its hind leg mainly. Increasing the torque had a significant impact, which gave enough strength to jump higher. The best performance was achieved when the ratio of the vertical velocity rewards to the front jump reward was set to 1 to 2, which gives nice balance between jumping and moving forward. The next task was high jump. Same as the standing long jump task, I put max torque to 5.0 because this is also a jumping task, so we need more power enough to jump. In this task, I use only 3 reward functions. The first one is vertical velocity reward, which is proportional to its velocity along the z-axis, which is upper side. It is used only when the value is positive, and the second one is soft rollover reward, which apply a penalty when the angle between the snapbot's local z-axis and the world z-axis exceeds 60 degrees. Last one was collision reward, which give penalty if there is self-collision. Actually, these 3 reward is same as the previous works. The final model for the high jump task achieved a jump height of 0.5 meters. Snapbot learns to use all 4 legs and to exert more force in the vertical direction than it does during the standing long jump task. Increasing the torque has a significant impact in this task too. And simple vertical velocity rewards outperform a complex milestone-based reward design. The last task was running sideways. For extra setting, I set a minimum alpha to 0.03, which make extra exploration opportunity. And in this task, I use 5 reward function. First one is velocity rewards, and it proportional to its velocity along the y-axis. And second one was heading vector reward, which encouraged the snapbot's forward direction to remain aligned with the x-axis. Third one was lane keeping reward, which discouraged shifts along the x-axis, so the snapbot could only move with the direction of y. And fourth and fifth one is simple. First reward is collision reward, which give penalty if there is self-collision. And the last one is rollover reward, which gives penalty if snapbots roll over completely. The final model of this running sideways task reaches the 5-meter targets in just 6.32 seconds. Snapbot in this task learned to move its four legs in sequence properly. It showed better performance when applying a single velocity reward rather than using multiple complex rewards designed to induce movement along the y-axis. And for the insight and challenge that I encountered during the training setup, in both jump tasks, it was very difficult to get the snapbot to initiate the jump initially. It often just stick to the floor and just never jumped. And in the running sideways task, it was difficult to maintain continuous walking over time. Snapbots frequently stopped moving in the middle of the task, and it was a very bottleneck for this task to be trained. And overall, simple and intuitive reward design often yield higher performance than heuristic and complex reward design. I tried many types of heuristic reward design and tested many versions of the reward system. And as the presentation shows, most of the best performance reward system was very simple. And that was the end of my reinforced learning project presentation, and thank you for listening.